Today I'm going to talk about a couple of libraries I've been working on under the title of Probing the Unprovable and Proving the Improbable. There's a bit of wordplay going on here. This is going to be a talk which talks about both types and tests as two different ways of improving basically the quality of software that we write, to reduce bugs, reduce unexpected things happening. But it's not going to be a talk about types versus tests. That's been done a few times already, and I already believe in types more than tests. But I'm going to show you how they're both useful for different things and in different ways. So this is a talk about types and tests, using types to prove the provable, and using tests to probe the probable or the probable. And these two words, prove and probe, they have the same root. One of them regards absolute certainty, provability. The other concerns probability, not absolute certainty. If we can't prove something, we can still probe it. We can test it. So probe means to test, basically. German speakers will know probieren as the verb to test. I think Polish is wypróbować, maybe. But probing doesn't prove anything. So if software passes the tests, the probes, then we can say that it probably works, not that it provably works. And this is the name of the library, probably, because it will show you, and the name is meant to remind you that at every opportunity, that your tests will only go so far. They will only tell you that something probably works, and hopefully encourage you to write tests so that your code provably works, if that is possible. So when do we test? When should we be using testing instead of types? First of all, there's no point testing things that are already covered by your types. If your types enforce some constraints, you don't need to test them. And we should take advantage of the type system where we can, but when the type system is not able to encode the constraints we have, or maybe it's just too difficult to use it in that way, this is where tests become useful. Now, I make the point that probably is a test library. It's not a framework. And this is a very important point. So why am I so concerned about this description of it? What is the critical difference, in my point of view, of between a library and a framework? Well, the library, as a library, it's designed to be maximally orthogonal to other libraries. And in a few claims, I will say why I believe that to be true. Tests are expressions or statements. These are two of the most fundamental concepts in Scala, most low-level ideas, expressions and statements. Every single line, more or less, almost, contains one of those at least. The checks on the tests are simply Boolean predicates. They're a lambda from some type to a Boolean. And suites, collections of tests, are themselves tests. So they compose. So let me just show you an example test. This test first of all, uses a runner object. This is what this test thing is. And the apply method takes a name string that represents what this test is doing. It has a body, which is going to produce a value of some sort. Here it produces an integer. And then we check the result of that body against a predicate. We check that we add two numbers together. We have to. This is just going to test one example of a number 3, and it's going to check that if you add two of them together, it's obviously true. It will give us that it is even. Now the return type of this test is int, because that's what the body returns. So this is just an expression. And when the test object called test has run some number of tests, we can run the report method on it, and we get a report back which tells us which tests were successful, which ones failed, and so on. That's it. That's more or less everything that happens. Now, the slide on the screen at the moment says something that seems very obvious, and it really should be one of the most obvious things about any code. Probability tests are evaluated when the program evaluates them. It seems obvious, but so many other test frameworks well, maybe not even starting, but certainly JUnit, would use interesting techniques like reflection to detect the tests. It wouldn't run them from the start of the program to the end of the program. It would reflectively identify which were the tests, and then it would invoke them. Probably doesn't do that. It just runs the program exactly the way the program would run if the tests weren't there. It's normal code. A test may be in the code, yet still not run, if that piece of code doesn't get run through the normal evaluation on the JVM. It may be run more than once, in which case probably will collect the result more than once. In fact, they may be run at any time, non-deterministically, in response to some stimulus, within any application at any point. Tests are just expressions or statements. I'll write it here again. This is as fundamentally simple a concept as it can be, and I think as it always should have been for testing. So let's look at some examples. This might get a little bit silly, but all of these are really potential examples for where you could run tests in the main method. This is probably the obvious one. You want to run some code, get some test results at the end of it. On the right-hand side of a case clause, if that particular clause gets matched, then it runs the test. You could run one in the REPL. You could have a test that gets run when a certain request comes into a web server. In fact, every time that request comes into the web server and captures the success or failure of some action. You could have it in a class constructor. You could have a test inside another test if you want to play around with it. You could have it on the right-hand side of a lazy val. So when that lazy val gets evaluated, not before the test gets run. You could have it inside a future. You use whatever method of parallelization you like to run the tests. The inside an actor, it could be inside the extractor to a pattern match. It could even be inside a macro that runs at compile time. This is because all I'm describing here are types of code that may exist somewhere in a code base. And probability tests are completely orthogonal. Now, I mentioned that tests are either expressions or statements. And this is a choice. This is a choice for the user who's writing the tests. The test expression uses the method check. So we define the test here, call expression, we do something trivially simple, and we check that it gives the right answer. And this will return the results, as I described before. This expression returns 2. But if we use assert instead of check, then we get a test statement. And this looks almost identical apart from the word assert instead of check. And that returns unit. Now, a statement test has the advantage, maybe, that it can be skipped by the test runner if you don't want to run it. I'll show you an example of that later, but let's talk about the test runner itself. The test runner has methods for creating and running a test, We've seen those used already. It records the results of those tests. Every time a test is run, it records them as a side effect. And it produces a report of the test results at the end. And you decide when that report gets produced. Now, maybe you've noticed there's a naughty word in this slide. Side effects. Is it acceptable to have the test runner causing side effects? Well, I would argue that the convenience of defining it this way is worth the extra thought required to check that they're safe. And that thought is not very much. The test runner, apart from the report method, which gives us the result of the test, it is write only. So all of the methods mutate it, but there's no way of getting the values out of the test runner until the end when we run the report. Now, unless you decide to write some code in your application that depends on the report, and you probably know you're playing with fire if you do something like that, and it also just wouldn't make sense. Unless you do that, the side effects are safe and well contained. This is actually a great advantage of Scala. It allows you to do this for the cases where it's convenient. Probably also provides a command line interface. This is very simple. It's just an abstract class which has a main method, and you provide a run method that goes with that. The run method takes a runner and returns a unit. So when you define that, you would specify your run method, and you would use the test value, the runner, to create new tests, specify the body and the checks, and then when that method completes, when run finishes, the CLI interface will simply print a report of what happened. It also does things like reads a few command line parameters. If you specify one of the tests you want to run by itself without running everything, then it will just run that test. Now that works for statement-based tests only, not for expressions. Now the reason why that is the case is that we can't, if a test is returning an expression, that expression may be used in the normal running of the program, bearing in mind that our tests can appear anywhere. That is that means it's not possible to skip running them. The code inside the expression must be run. We need the value to come back in order to run the program. However, if the test is returning unit, if it is a statement test, in that case, we don't need to actually run it. So for the typical unit tests that you may have written with JUnit or Scala test, they can have an assertion, they can return unit, and the runner will choose to run the ones it needs to, and it won't run the ones it doesn't need to. Here is an example of the command line interface being used. We define an object called myTest. We define the run method. I've only defined a single test, and it does something not particularly interesting, but we're not really looking at the content of the tests here. But this will run the test, and at the end of it, it will produce some results. And here is an example of the output you might get. Hopefully this will come out okay on the video. The text is maybe a little bit small, but these are the tests of probably itself. They all pass, which is good. And each test has a name. We record the time it took to run. And we might also record some debug parameters, and I'll tell you about those in a second. And we also have a hash for each one. Now, rather than typing in the full name of the test every single time we need to refer to it, we can use the hash, which is just nothing more than a hash of the name. It's a convenient short way of referring to the test name. And there's a few possibilities. A test can pass or fail. An exception may be thrown either during the body of the test or when it shouldn't really happen. It's not desirable, but it may be thrown when running the check. It might be a test that is run multiple times and succeeds a few times and then fails. And it might be that the test is actually composing tests from a suite, and some of the tests in that suite pass, some fail, in which case we get a partial response back. Here's an example of a test that runs multiple times. I literally put the test inside a for loop, and I run it 10,000 times. And you'll notice that I've added a parameter called iteration equals I. I picked the name iteration for this example. You can choose any word you like to describe a parameter there, because it uses the dynamic trait to allow you to specify some number of debug parameters with names you choose. And you can supply them as additional parameters to the test. If the test fails, in the debug column, as you saw on the previous slide, you will see the value that caused it to fail. It'll say iteration equals, for example, 52. We can also do property-based testing. And I know that there have been a lot of talks on how this works with Scala check. It was actually very, very easy to implement for Probably. Simply because we can run tests multiple times, and all we need to do is stream some data across the test and record the results. And there is some code that uses Magnolia. I don't know if you know my other project, Magnolia, for generic derivation of types, but it'll automatically generate the arbitrary instances it needs to generate this stream of random and different persons, so that we can test them all. And here's an example of a suite. Now, the signature of the suite method is very similar to the signature of the command line application. And we have the test object called test, the test runner called test, which will run a suite when it when we reach this point in the code, and it will run these series of tests using the test runner that I've called JSON test. And it does something very trivial here. You can see the first test actually returns a value. It's an expression test, and then we use that value in the next test. So this is an interesting way of potentially chaining them together. And when the results are printed, if you're in a nested suite of tests, the way the table is printed, they will be indented slightly so that you can see that they're grouped together in some way. I didn't have time, unfortunately, to produce an example of a screenshot of that, but that is what happens. And you can nest test suites within test suites within test suites. They form a tree. It's composable, recurses infinitely if you want to. And I mentioned that the command line interface is very similar to the signature for the parameter to the suite. You can simply pass in an application as a parameter to the suite method. So just to wrap up on what would be the first half of the talk on Probably, it's an experimental library and it's available on GitHub. The source code is there. You can compile it at the moment only using Fury. If that means nothing to you, then you will have to wait for me to publish a binary later this weekend, which is at the top of my to-do list once I finish this talk. And having spoken about tests, I'm going to swiftly move on to the second half, which is about proving the improbable. And all that talk about testing actually, I want to reduce the amount of testing we do in general. I don't like testing as much as writing types. With types, the compiler's helping you all the way. It's helping you maintain the code when that changes. Tests don't do that. You have to maintain the tests separately from the code. So I really want to use the type system as much as possible. I want all exceptional cases to be handled properly. What I mean by that, noting that exceptions are not impossible, they might be improbable, they might be the non-happy path, but they're certainly not impossible. They may occur quite frequently. But the way we write code, by default at least, suggests that they maybe don't even exist. We're not forced by the compiler to handle exceptions. We can, but by default, the compiler, be it Java or Scala, doesn't force us to handle them. Now, this makes for some quite concise code that, if it is on the happy path, it's great. It'll work for a script, but you don't want to deploy that to production. Now, actually, the compiler could help us a lot more. It knows a lot more information statically than, in most cases, we take advantage of. And I want to show off a library called Ouarantine, which is at the opposite end of the spectrum from Probably. It's heavy on types and not simple in the same way that Probably is. You may be amused by the name Ouarantine, and you probably think, well, John's been locked in quarantine for the last 2 months and couldn't think of a better name than Ouarantine for the next library. Actually, the library was named back in October last year, so it might be less topical than prescient, but it is what it is. Let's talk for a second about partiality and totality. So any expression in a program may be partial or it may be total. If it's total, then whatever input we give to that expression, we will always produce a result. We won't throw an exception. This is good. This is what we want. With a partial expression, there exists some inputs, or there may exist some inputs, which don't produce results. And these are harder to deal with. That's not to say it's they don't have uses, but in general, it would be life would be easier if we're only dealing with total expressions. So if we're only composing together total expressions with each other, that gives us a complete total program, and we know that whatever input we give it, we get some output. Now, from a modeling point of view, if you're developing a production system to work on in some real world domain, we can use types as a very, very general purpose and a rich way of representing constraints on the objects and values that we use in that domain. And one of the most fundamental choices we can make when modeling a particular domain is to make invalid states unrepresentable, to make it absolutely impossible to write the code or represent the code at runtime, or the data at runtime. That would be an impossible state. We don't want to allow that. And if there's no way for that impossible state to be represented, we're good. And if we're composing only total functions from only possible states to other only possible states, then there's no risk that we end up in a situation where the program is representing something that doesn't exist, that is not existent in the domain. One final slide on exceptions. These are basically the JVM's way of encoding partiality. And they do serve a purpose. They allow the program to continue running in some way if we end up in a situation where a particular input is not handled. Now, the program doesn't just stop instantaneously. It starts dropping stack frames until it reaches some point where that particular kind of exception is handled, and you recover from it. It's a fallback, but it gives us it allows the program to carry on in some way. But by default, we're not forced to think about how they're handled. And I think in general, we would like to be in many cases, certainly in our production systems. So let's go to a very, very basic starting point, option of t. Option of t gives you totality as a return type for something that would otherwise return t. We can represent the exception as none, and we can represent the success value as some t. That's good. It's good, but it doesn't give us access to the exception. We need to do something like try to actually record the exception at runtime. And try may be a success or a failure. If it's a failure, then we can get access to the object, the heap object that represents the exception. We can inspect it, we can look at what kind of exception it was, and deal with it in different ways depending on what the exception was. That's better. But all we know when we have a try is that it was, in fact, a throwable. Some sort of throwable occurred, but the compiler does not statically know, given an instance of a try, it doesn't statically know, for example, that it could only possibly be an IO exception. That's not encoded in the type. It's lost at the point of creation. So what we often do, especially since either became right biased, is that we use either to represent either the left branch of the failure exception, or a right branch, which is the success value. And this is better. This is closer to an optimal representation of the static information we want to record for a return value. Here, E is the exception. Now, in an actual usage of this, it may look more like this: either of IO exception, int. And every time you need to refer to that value, you need to specify either of IO exception, int. And this is the part of it that stands out most to me. Partly because it's longer than the word int, but this is very much noise. I want to focus, at least as the programmer, not necessarily the compiler, but I want to focus on int instead of IO exception. So in Ouarantine, this new library, I propose a type called results. And I propose that I can represent this same information that's in either using a path instead of the parameter. And furthermore, if we import that path, import from that path, we can actually just refer to it as result of int. This is much more readable. It's much more focused on the success case, but we don't lose the tracking within the compiler, the static tracking of the exception type, the precise exception type that this is encoding. Let me show you how this works. This is a hypothetical, vastly simplified example of or indicative, shall I say, of the API for results. I wanted to show that there are some methods will return a type that's dependent on T, some will return a type that's dependent on E. Now, starting from a result definition that is isomorphic to either. So this isn't the one that's in Ouarantine. This is one that's equivalent to either. We can start to make some changes to it to transform it into the same into the result type that's in Ouarantine. So the first step, I'm going to add a class called domain, which has an E type, which is an exception, and I'm going to add a value to my result, which is a reference to that domain. So bear with me on this. Might not be obvious where I'm going, but given a domain, given a ref that points to that domain, when we instantiate a result, the compiler will instantiate the type E from the domain. It will infer it from whatever type of domain we're using, and that same type will be used as the return type of failure. Now we can go a little bit further and change that type from a type parameter to type member. So domain loses the type parameter. The parameter to result is now domain, and the way we write that same type as the return type of failure is ref.e. We can refer to the value of the parameter, and we can refer to the member type E within that. Now this is equivalent to the previous slide. I've just switched between type parameters and type members. The logic that goes on inside the compiler is virtually identical. The next thing I can do is I can put result inside domain. And I've actually renamed ref to outer, because this is the reference we get for free when we define an inner class. Now you maybe not aware of this because it's more of an artifact of the bytecode, what it compiles down to. But every inner class contains a reference to its outer class called $outer. It's a synthetic value, and it's usually hidden from you. So we don't actually need to include that outer reference there. We can write it like this. So I've made result a member of domain, and I can actually switch domain back from having a type member to having a type parameter. So the signature of result doesn't reference E, but an instance of a result, which must be dependent on an instance of the domain, does. So we can create a domain like this, new domain, and it can be a domain over IO exception. So this is a domain in which the kind of exceptions we expect to get are IO exceptions. And we can construct a result from that. It's an integer. And to make it just a little bit easier, if we import from that domain, we just write result of int, and that's what we get. You'll notice that the right-hand side of the bottom line is an answer. Answer is one of three case classes that inherit from results. This is closer to the definition of results in Ouarantine, still vastly simplified, of course. So answer, error, and this maybe interestingly named type called surprise partition the possible results. If you have a result, it must be one of these three. So what are they? Well, answer is the success type, or right, or sum. It is completely isomorphic to those cases. It's the successful value. Error is an exception. It captures the exception. but it only captures the exceptions that we expected. It captures the exceptions that are encoded in the domain within which that error is defined. So in that IO exception domain example, we could have an error of an IO exception, but the reality is that other kinds of exception can occur. You may get an arithmetic exception happening within a result handler, which would be a surprise. Nobody likes surprises, but we want to capture them if we can, in the same way that try will capture every exception that gets thrown, apart from non-fatal ones. And the same is true of results. So we split our exception types into the ones we're expecting and the ones we're not expecting. And if a fatal like Stack Overflow exception is thrown, then that doesn't get caught because that's generally going to produce more problems. Let's look at a real-world example. Parsing a string into a dynamic JSON object. Parsing can produce a parse error. That is one kind of error that you may get from parsing, probably the only kind. If we have a JSON object already, we might imagine that we have the value is missing, so we can't get it. It might be there, but it's the wrong type. Or it might not be valid for that particular type that you're trying to extract from the JSON. Now, this is all hypothetical JSON library. But we have different kinds of exceptions thrown by different methods. And we could even have a method which goes straight from a string to extracting a value from that string, which could be any of these exception types. So there's a lot of code on this slide, and I'll talk you through it slowly. The highlighted text at the moment shows you the structure for our exceptions. This will be defined inside the JSON library. So we have a JSON error and an extract error as sealed traits. And then we have 4 case classes which represent exceptions that may be thrown. And I've categorized them into JSON errors and extract errors. And then a little bit down from that, I define 3 different domains, a parse DOM, extract DOM, and JSON DOM, representing a domain of possible errors. So there's the domain of errors that occur during parsing, the domain of errors that occur during extraction, and then this general JSON DOM that, if you look at the type, the sealed trait JSON error, any one of those 4, or every one of those 4 exception types is a subtype of JSON error. And at the bottom, I've defined 3 methods, parse, as, and parse as. These would occur somewhere in the API. I'm listing them all in the same place just so you can see them, but imagine them defined on different objects. And the return types of these are all results, but they're results that are parameterized on the particular domain, which represents the possible exception types that may be thrown or may result from that particular method. And this is encoding the same information as we had in a version that used either, for example. Now, this is an example use of a method called recover, which is one of the methods of result. Result has a whole variety of methods. And recover, what that will do is it will look at, it'll deal with the case where we have an exception that's been captured as an error. So if it's invalid, we're going to recover that into a string, and we're just going to use the string called error. If it is a missing value, then we're going to use some sort of default instead. And if it's the wrong type, then that is also considered an error. Now, I don't know if it's desirable to write the word error in a string and return that. But this is what I wanted to. This is a simple way of illustrating how this method works. That's great. It'll compile with no errors and no warnings. And it compiles fine simply because we've handled all of the cases. And the compiler knows by virtue of the return type of as, it is a result in a particular domain that is parameterized on a sealed trait that is the supertype of exactly 3 cases: invalid, missing, and wrong type. And if I were to forget to include wrong type, or any of the others, that would result in a warning, or if you have fatal warnings, a compile error. This is telling us statically, before we get to the runtime, that we need to handle this type if we want our expression, the expression you see on the screen now, to be total. There are some other methods defined, and this is certainly not all of them, but result offers a few possibilities. If you have a surprise, the middle bottom circle here, in domain 1, so D1, we can mitigate that into an error. So if you had an error, if you had an exception thrown that we weren't expecting, maybe we want to wrap that in some other error type so that we know that we don't have any unknown exception type to handle. We can recover from an error, so d1.error, that can be recovered to a d1.answer. We can map from an answer of t to an answer of s. That is the map method you're familiar with. And likewise, we can map from an answer, d1.answer, to a d1.result, because we may be mapping, flat mapping, into an error type from an answer. So it could be not a success, or it could be a failure. That will produce a result in domain D1. We can then adapt that, if we wanted to, from one domain into another domain. That means we need to provide translations from one collection of errors into another collection of errors. And this is just a subset of the methods that are available. There are methods for transitions between all of these various different combinations of domain and type parameter and error, answer, or surprise. So, if you have quarantine in if a library uses quarantine, for example, the JSON library, if you're a library developer, what you want to do is carefully design domains that prescribe the set of exceptions that may result from executing each and every method in your library. That is quite a burden, but this is what libraries are for. They put the burden on the library designers to implement this once, so that at the use sites, which should be much more numerous, at the use sites, we don't have to worry about it. So application developers, these are the usages. If you want to adopt quarantine, what you would probably do is define just one domain. It is the domain that encodes all of the exception types you want to represent in your application. As a sealed trait, because we need the sealed trait for exhaustivity. And then you can define implicit adaptations. There is a type class instance, there are type class instances which you can create, which will convert automatically from, for example, a JSON domain into into your own domain. You can define these once globally, maybe in a package object. And there may also be particular cases where we are dealing with a result from a different domain as a one-off. We want to handle certain errors in certain ways, map them to certain errors within our own domain. And at every stage, the compiler is checking for us that every single exception type that we believe each method will throw is handled and dealt with. And if we forget one, we're told. And what this gives us is totality over the methods that we are using, which means we can more safely reason about what our code is doing. So just before I wrap up, a few details about Ouarantine. It's available, it's still experimental, but it's available on my GitHub page. The source is at that address, github.com/preventive/Ouarantine. And it's Apache licensed, as was Probably. And if I manage to get the Probably binary published, I will also almost certainly get the Ouarantine binary published as well. And that is all I have from the presentation. And it fitted into almost 45 minutes. And I'm now ready to take questions. So thank you for listening.
Okay, we have two questions. Sorry, I was muted. The first one is, can cats monad instance be defined for a domain result?
A cats monad instance, you would need one for each domain, but I believe it's possible, yes. And you could maybe even, yes, it might even be possible to define a polymorphic one that, yeah, I think you probably do. Yeah, I'm not overly familiar with the cats monad type, but I mean it's a monad. So yeah, I believe that's possible. Yes.
Okay, and the second one is, can a monad transformer be defined for domain results?
Well, it is a monadic type, so I think the same answer applies. I generally avoid monad transformers if I can, and stack to them. But yeah, the signatures conform to the monad laws, so this should be entirely possible.
Okay, so that was the questions that we had from YouTube chat. Thanks for your presentation.